So today we're going to start chapter 12, which is all about solutions. So what is a solution? A solution is a homogeneous mixture of two or more substances that exist in a single phase. And what we mean when we say existing in a single phase is it's uniform throughout or it has the same composition. So an example of a homogeneous mixture or a solution is things like Kool-Aid, salt water, ocean water, so salt water again, or sugar water. And when we're talking about sugar water or Kool-Aid or ocean water, we're going to say, specifically for a sugar water example, sugar is soluble in water. Kool-Aid is soluble in water. Salt is soluble in water. And what we mean when we say the word soluble is we mean that it is able to be dissolved in our solvent. Now, talking about solvent versus solute, so solute is the substance that is dissolved in a solution. So think of it as, the thing that you're adding, or we specifically refer to it as the component that is present in the smallest amount. So the component that is smaller amount. So whatever you have an excess of, whatever you have a lot of, that is going to be your solvent. So it is your dissolving medium or the substance that does the dissolving. And the thing that is dissolved is going to be the solute. So just two terminology that we are going to use throughout. They sound very similar. Solute, solvent, soluble, solubility, solution, all of it sounds the same. So just make sure you're paying extra attention in order to keep it straight. So using our Kool-Aid example, the solute is that packet of Kool-Aid, whereas the solvent is water. Back in our sugar example, sugar water example, sugar is the solute and Kool-Aid water is, or not Kool-Aid water, I was reading the slide, my bad. Water is the solvent. When we're talking about ocean water, water, again, is the solvent, and the solute are all of the ions that happen to be dissolved in the water. So we have several different types of solutions. So your typical solution that you're going to think of is something in the solid phase that's going to be dissolved in water. That's the most common solution that comes to mind when we're thinking about solution. But we have many different types of solutions. We can have gas and gas, gas and liquid, 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 solid, solid, liquid, solid, solid. All sorts of things. And I actually want to point out that a solid-solid solution is called an alloy. So when you have two metals mixed together, like copper and nickel, it's going to make an alloy, and that is a mixture or a solution of those. So what we see quite frequently is we see solid in liquid. So the solute state is a solid, and a solvent state is a liquid, such as in sugar and water. But as you can see from this table, there are many different types of solution, and solutions do not exist within a certain phase. They don't regard only certain phases and exclude other phases. It can happen between any of the phases in any sort of combination. A suspension, on the other hand, is a heterogeneous mixture where the particles in a solvent are so large that they're going to end up settling out of solution unless you add some sort of manual agitation or stirring of the solution. And in this example, the particles can end up actually being separated by a filter. And a good example of this is a jar of muddy water. An example of this that should be familiar to all of you is when we do precipitation reactions in lab. So when we mix our two initial aqueous solutions and we get that lovely suspension, it appears that we have another solution. But if you let it set for long enough, your precipitate is actually going to settle out of solution and is going to sink to the bottom. And we could agitate it again, we could stir up the solution, and it would appear to be homogeneous, but eventually, with time, those particles will settle out and we will get that heterogeneous, that separation of our particles. So a precipitation reaction is a great example of a suspension mixture as well. The product of a precipitation reaction is a suspension. So I want to talk about three factors that are going to affect the rate of dissolution. So dissolution basically means dissolving. So the rate at which something is going to be able to dissolve within a solution. So the first thing of that is increasing the surface area of the solute. So increased surface area of the solute will increase the ability of the solute to be dissolved. And the reason why increasing the surface area allows for increased dissolution of the solvent or solute in the solvent is because it's giving more surfaces for the solvent to come and attach to the particles of the solute and pull them into solution. So when we talked about things and certain interactions within different particles within a solution, that's what's happening here, is the solute with a larger surface area has more planes for the solvent to come in and kind of take pieces of the solute into solution. So agitating the solution is going to affect the rate of dissolution. So stirring or shaking is going to help disperse those solute particles and thus increasing the contact between solvent and solute particles. And that contact is what allows for them to be dissolved. So stirring really just disperses them, makes it more even, and kind of introduces maybe some of these solute particles that weren't near solvent particles. So it helps to kind of even things out and allow for that dissolving. And then the last thing that's going to affect it is heating up a solvent. So higher temperatures means we have particles that are moving around faster. So when they're moving around faster, we have more collisions between our solvent and solute particles, and thus that allows for increased dissolving, but also moving around quicker is going to help disperse them more. So that will also help the dissolving process. So affecting dissolution, so if you add a spoonful after spoonful of sugar to tea, eventually no more sugar will be dissolved. So the point at which this limit is reached for any solute-solvent combination is going to depend on one of three things: the nature of the solute, the nature of the solvent, and the temperature. So when maximum solubility is reached, molecules are returning to the solid form at the same rate of which they are going into solution, and that is known as solution equilibrium. So if you recall, we have talked about equilibrium before. Basically, equilibrium is a state in which our forward and reverse reactions are happening at the same rate. So our forward reaction in this scenario would be the rate at which we are dissolving our particles, whereas our reverse reaction would be the rate at which our particles are then falling out of solution. And this happens in a saturated solution. We have reached that maximum solubility. So a solution that contains the maximum amount, as we just talked about, is a saturated solution. So if you are adding more solute to a saturated solution, it's saturated. It's unable to hold that solute into solution, so it will be unable to dissolve. I want to make this very clear, under the current conditions. Yes, we are able to change the conditions such as pressure or temperature, and we will have a change in whether or not it's able to dissolve. But under these current conditions, that is our given state. So this is because that equilibrium has been established between the ions leaving, so the ions that are falling out of solution, versus the ions that are entering into the solution. So a solute that's going to contain less solute than a saturated solution is simply called unsaturated. So it's called unsaturated up until the point where it has reached that max, and that max is called the saturated solution. So after the saturated solution, there are ways, as I said before, to actually end up dissolving more. So a solution that contains more dissolved solute than a saturated solution contains under those same conditions. So usually to get a saturated solution, you have to change the conditions, but if you bring them back down to the same conditions, then it is possible to have a supersaturated solution. So if you cool a saturated solution, the excess solute usually comes out of solution, leaving the solution saturated at the lower temperature. But sometimes the excess solute doesn't separate, and then you get this supersaturated solution. Another way to do so is to actually heat up the solution, so you're able to dissolve in more solute, which we have already talked about, so that should make sense why that works. And then when you cool it back to this normal baseline temperature, sometimes your particles remain dissolved. And that's when you have a supersaturated solution where you contain more. So it goes unsaturated is under that sort of max, saturated is the max, and supersaturated is beyond the max. So sometimes it doesn't separate and you get that supersaturated solution, and a supersaturated solution will form crystals if disturbed. So just think of it as everything is in this really nice blend, and disrupting that blend in any way, shape, or form will kind of cause those solute to fall out of solution, and when they're falling out of solution in a supersaturated state, there's so many of them that they're actually going to help crystallize the solution. So we have an electrolyte versus non-electrolyte. So this is specifically referring to solutes that are dissolved in a solution. So when a substance that is dissolved in water is going to be able to conduct electric current, that is called an electrolyte. So any ionic compound is able to conduct electricity. In order to collect electricity, you need to have free-floating electrons. Ions have free-floating electrons, so they would be electrolytes. So any ionic compound is going to be classified as an electrolyte. So the positive and negative ions separate from each other and are free to move. So that free movement makes it possible for the electric current to pass through the solution. So a substance that's going to dissolve in water that is not going to conduct electricity is called a non-electrolyte, so just the opposite of an electrolyte. And sugar is a good example of a non-electrolyte. Sugar is a pretty neutral molecule. It's composed of lots of hydrogens and lots of carbons. That is not a ionic bond. It's actually a nonpolar covalent bond. So the nonpolar covalent bonds between the carbons and the hydrogens don't really want to dissociate in the water. And we do have some oxygens that will interact with the water, which is what allows it to dissolve, but it is not enough, and sugar is not an ionic compound, so it's not really going to break into anything smaller. So you just have individual sugar particles in solutions, and those are not going to be able to conduct electricity. So neutral solute molecules do not contain mobile charged particles, so a solution of non-electrolytes cannot conduct electric current. I think we kind of talked about that a lot on this slide. So pretty much the way to tell whether it's electrolyte or a non-electrolyte is just identify if it's an ionic compound or not. So if it's an ionic compound, it will be an electrolyte. If not, it's going to be a non-electrolyte. So a substance that is the dissolving medium is called the solvent. The solution is the combination of the solvent and the solute. The solute is what you are adding to the solvent, so the thing that is getting dissolved. And soluble is a term that we use to describe whether or not things are able to be dissolved in one another. So which of the following types of compounds is most likely to be a strong electrolyte? Remember, when we're talking about strong electrolytes, what do we want to think about? An ionic compound. We want that complete dissociation because it allows us to have free-floating electrons, which allows for electric current to pass through the solution.